comparisons of series. So in this section, we're going to learn two comparison tests, the direct comparison test and the limit comparison test. And the idea of those tests is to compare a given series with a series that's known to be convergent or divergent. Okay. So the first one, which is the direct comparison test, suppose you're given two series. The first one whose terms are ANs, the second one whose terms are BNs, and suppose that the ANs are all positive and they are dominated by the BN terms. Okay. Then, if the series whose terms are Bn converges, it follows that the series whose terms are An is going to also converge. So if the series whose terms are dominating is finite, has a finite sum, then this is the same what's going to happen for the series whose terms are the smaller terms. Okay. I'm not saying they're going to be the same sum. I'm just saying that if one converges, if this is a finite sum, then that's going to be also a finite sum. I'm not saying that the sum is going to be the same. All right. The comment here, the direct comparison test is equivalent to the failure of that forces the failure of this, right? So if under the same hypothesis, obviously, if the series whose terms are An is divergent, then the series whose terms are Bn is also a divergent series. Okay. All right. So how does the proof go? What's the setup? The setup is I have this for all n. I have this double inequality for all n, and I know that the series whose terms are Bn is convergent. Correct? So we're gonna denote for all n, we're gonna denote Sn to be the nth partial sum of the series whose terms are An. So concretely, I'm saying that Sn is defined to be the sum of all the AIs where I runs from 1 to n. So Sn is A1 plus A2 plus A3 all the way to An. Furthermore, I know that this series is convergent, which means that this is a guy that's known. It's a finite number, this sum. Let's call it L. Correct? Since it's a finite thing, let's refer to it as L. This L is a finite number, which is representing the sum of the series. Okay. Now, as we said, we have this compound inequality here that holds for all choices of n. Since this holds, what can you say about Sn? Well, the lower bound implies that Sn is increasing, or non-decreasing, to be more precise, right? Sn is non-decreasing because of this lower inequality, correct? Technically, what I'm saying is, let me zoom in a little bit. What I'm saying is this: Sn plus An plus 1. This is certainly bigger than Sn. Why? Because of this inequality, correct? So every AI is positive. For any n, every AI is positive. So adding to Sn an entity AI, so you're increasing that entity, correct? And this guy is Sn plus 1. Agree with me? So certainly Si, the Si sequence or the Sn sequence, is a non-decreasing sequence, correct? Furthermore, Sn is bounded because of this, the Sn is bounded above by the nth partial sum of the Bn sequence, the series, right? So also we have that Sn is less than or equal to the summation of all the Bi, and in here I have I runs from 1 to n. Why? Because every term in this nth partial sum of the series whose terms are ans, each one of them is dominated by Bn. So S1 is dominated by, A1 is dominated by B1, A2 is dominated by B2, and so on. So the sum A1 plus A2 all the way to An is bounded above by B1 plus B2 plus all the way to Bn, correct? And since every Bi is positive, because every Bi is bigger than An, which itself is positive, so certainly Bi is positive. So that's going to be less than or equal to, L. Why? What's L? It's the sum of the full series. So certainly the full series dominates this partial sum. It's a finite thing. Obviously L contains those terms and a lot more, right? So one more time. The series, the full series contains this nth partial sum and a lot more. As you see here, n goes from 1 to infinity. Certainly it contains those which are between 1 and little n. So this guy is bounded above by L, which is a number, which is a finite number, because the series Bn converges. Correct? So this holds for all choices of n. So this is for all choices of n. So Sn is, on one hand, non-decreasing and bounded above. As such, by the monotonic sequence theorem, Sn is going to be a convergent sequence. Correct? And if the sequence of partial sums converges, then the full series is going to be a convergent series. Makes sense? So what did we show? What did we show here? We've shown that under this hypothesis, if the series whose terms are Bn is convergent, then that's going to force the conclusion of the following conclusion. The series whose terms are An is also convergent. Okay. If you want to read, if you want to verbalize this result, you can verbalize it by the 3 lines that you see here in blue. Concretely, you can say, if a series whose terms are smaller, I'm talking about the An being the smaller, than those of a non-convergent series, the Bn's, then our series is also convergent. So if you know that the series whose terms are Bn is convergent, and you have another series whose terms are smaller, then that's going to be convergent as well. This is what the theorem is saying. Now, equivalently, the comment is saying, if we start with a series whose terms are larger, the Bn's, whose terms are larger than those of a non-divergent series, the series An, then it too is divergent, right? This is what the comment is saying. So if we start with a series whose terms are larger than those of a non-divergent series, so the Bn's are larger than An, and, we said the series An diverges, then the series whose terms are Bn, the larger one, is going to also diverge. So this paragraph is about verbalizing the theorem and its comment. Okay. All right. Let's look at this example. Determine whether the series, this one, is convergent or divergent? Well, let's apply the direct comparison theorem, direct comparison test. We would like to compare this series to something that's either convergent or divergent. Well, the dominating term downstairs as n increases is 2n squared. So let's compare this series with the series whose terms are 5 divided by 2n squared, just this part. Okay. So let's let me zoom in. So how do you compare 5 over 2n squared plus 4n plus 3 to 5 divided by 2n squared? How do we compare the two? Well, n is at least 1, right? N is a natural number. So the denominator here is bigger than the denominator here. So certainly the left entity is smaller than the right entity, right? We decreased the denominator, so we're going to increase the quotient. All right. And this is for all n. Correct? And certainly this one is positive. So certainly this is a positive entity. Okay, let me just move it a little bit this way. Correct? So this is a positive entity. So I am in the context of the direct comparison test. Namely, I'm talking about this being an and this being bn, right? You're going to tell me, oh, I have less than or equal here. Well, this is smaller than that, so certainly this is smaller than or equal, right? No problem with this. All right, you can keep it. We can just erase it. All right, so the idea now is, do you know anything about this? 5 divided by 2n squared, the series whose terms are those guys. These terms are constant multiple of, which is 5 over 2, multiple of the p series when p is 2, right? So, and we know that that p series when p is 2 is going to converge. So let me write the detail just as much as I can fit here. So we know that the series whose terms are 5 over 2 and squared, that series is the same as this series, 5 over 2 times the series 1 over n2, correct? And this is as n goes from 1 to infinity here. I'm not gonna write everything, so you got the idea. And this is a constant multiple. This is a constant multiple of a convergent series. This is the p series, right? The p series when p is 2. So this is a constant multiple of p series. As such, it's one of the properties we learned in the series section. That's going to be a convergent series, which is this. That's going to be a convergent series, right? So since this is a convergent series and whose terms are dominating another series, they're both positive. So by the direct comparison test, the given series is going to be a convergent one. Okay. So I'll let you complete the details, but I gave you the main ingredients. So one more time, we were given this series. We were able to find another series, namely this one, whose terms are dominating the given one, the terms of the given one. And that one, that the series whose terms are 5 over 2 and 2, is a convergent series because it's a constant multiple of a series which is convergent. It's a p series with p equals 2. So as such, by the direct comparison test, that series, the bn are these guys, right? So that series is convergent. As such, the series whose terms are smaller is convergent as well, which is the desired thing. Okay. All right. The red remark, it says the following: in the direct comparison test, in this test, this compound inequality here is written for all natural numbers n. Well, what this is saying is you don't need it for all of the natural numbers. You just need it from a certain rank onward. Why? Well, what happens if this only holds from a certain rank onward? For n bigger than or equal to n naught. You can run the same proof, but instead of starting at 1, you're going to start at this n naught, right? And at the end of the day, if the series convergent from n naught onward, the series an is going to be convergent from n naught onward, and hence the full series is convergent because again, you're going to be adding finitely many terms to the series which starts at n0 to recover the entire series, and adding finitely many numbers to a convergent series is still convergent. Correct? So what this remark is saying is that don't ask for too much if you can do it by a little less, right? You only need it from a certain rank on. So if you don't have it for all natural numbers, the test is going to be applicable as well. It may be applicable. So, all right. All right, and this is illustrated by the next example. This example is a series which is familiar to us. We've seen it in the previous section. We dealt with it using the integral test at the time. We showed that this function ln x divided by x is positive, decreasing, and continuous from 3 onward. And we discovered that this series is divergent at the time. Now we're gonna try to compare it to a series, which is, since we know it's gonna be divergent, to a series which is gonna be a divergent series. Correct? What do you think the series is gonna be? One such series can be 1 over n, because ln n is, if you take n to be bigger than or equal to 3, you can say that ln n is greater than 1, right? When is this precisely 1? When n is e, correct? But the n is a natural number in this context. So from 3 onward, this happens. And then ln n divided by n is greater than 1 over n for all n greater than or equal to 3. Okay. I'm going to start using this notation. This is for all. I've said it before. I was hesitant to start writing it, but it saves space, so I'm going to do it. So this is for all n bigger than or equal to 3, that inequality is going to hold. Okay. And now the series whose terms are 1 over n is divergent. This is the harmonic series. Correct? So since so probably it's worth writing here, it's positive, right? So by the direct comparison test, DCT, direct comparison test, and the fact that the harmonic series is divergent. Okay, let's be specific here. So this series starts at 3, is divergent. What do we get? We infer that this series is divergent, correct? And if this is divergent, you add, this means this is plus infinity, correct? This means this is plus infinity because all these terms are positive in this context. When n is bigger than or equal to 3, this guy is positive. So this is going to be positive infinity, and if you add to it a couple more, namely the first and the second term, this remains divergent. So adding finite number to infinity, that remains what is it? That remains infinity. So the whole thing is going to diverge, correct? So I'm going to let you complete the details. So probably one more thing you can write is that the whole thing is divergent too. Okay. All right, theorem 2, limit comparison test. Suppose that you have two series whose terms are positive. So all of the ANs and all of the BNs are positive. And suppose that the limit as n goes to infinity of this quotient, AN divided by BN, suppose that this limit is a positive and finite number. So suppose this limit is somewhere between 0 and infinity, excluding 0, excluding infinity. Then the two series, this series and this series, so this series whose terms are AN and this series whose terms are BN, are of the same nature. Either they both converge or they both diverge. Okay. How does the proof go? Since this limit is a finite and positive number, I can place it in between two positive numbers, right? So one more time, I know that this is a number that's positive and finite. So I can fit it in between two positive numbers, right? Let's call the lower one little m and capital one, and the upper one the capital M. Hence, so let me just show to you on a picture before I continue reading that. So let's give this guy a name. How about we call this guy L? So I know that L is between M and capital M, right? Okay. What do I also know? I know that AN over BN, so if you want to call this guy here XN, so call this quotient AN over BN XN. What does it mean that XN, the limit as n goes to infinity, XN equals L? This means XN converges to L, right? Which means XN is going to be sitting, the sequence XN is going to be sitting inside any neighborhood of L, any ball centered at L from a certain rank on, correct? One more time. If I know that the limit as n approaches infinity of xn is equal to L, this means that the distance separating xn and L can be made as small as one wishes as by taking n sufficiently large, right? Okay. So what this means if I take a neighborhood, let's say L plus epsilon and L minus epsilon, so I'm taking the ball centered at L, whose radius is epsilon, I know that this sequence xn is going to start being here from a certain rank on. So xn is going to start being inside this neighborhood somewhere. I don't know where, but somewhere inside, from a certain rank on for n greater than or equal to some number, and not. Correct? So xn is somewhere here. Well, if xn is somewhere here, certainly it's between m and between little m and capital M, right? From this rank on. Correct? And what's xn? It's this quotient. So this quotient, an over bn, is going to be in between m and little m and capital M from a certain rank on. And this is what this next line is saying. This symbol here means there exists. So this means there exists. And as we said, this one means for all, right? I said it before. So there, from a certain rank on, so there exists a natural number n0 such that for all numbers that are bigger than or equal to n0, right? The xn, which is an over bn, is going to be between little m and capital M. That's what we have. Correct? Now, if you multiply both, all of the three sides by bn, you get this. So you get this double inequality for all n that are at least n naught. Okay. And now we're done, because what we need to show is that the series whose terms are an and the series whose terms are bn are of the same nature, right? Look, if the series whose terms are bn is convergent, so is the series whose terms are capital M times bn. And then by the direct comparison test, keep in mind that the an's are positive, right? All of the terms are positive here. So the direct comparison test applies. As such, the series whose terms are an is convergent because its terms are smaller than the series or the convergent series whose terms are m times bn. Correct? Now, if bn if the series whose terms are bn is divergent, so is the series whose terms are little m times bn is going to also be a divergent one. And then by the direct comparison test, this is a positive number, right? Because little m is positive and the bn is positive. Every bn is positive. So the direct comparison test also applies if I assume that bn is a divergent series. Sigma bn is divergent. The direct comparison test applies, and it tells me that the series whose terms are an is going to be also a divergent series. Okay. So the direct comparison test actually implies the limit comparison test, as we see in the proof, right? We needed the direct comparison test to imply the limit comparison test, or to show it. All right. So let's read this one more time. Theorem 2. If you're given two series whose terms are positive, and the limit of the ratio between the terms, so the limit of the ratio of the terms of the two series as n goes to infinity is a finite number that's positive, then the series is going to be, the two series have the same nature. So either both of them are convergent or both of them are divergent. Okay. Let's read example 3. Determine the convergence of or divergence of the series whose terms are 1 over 2 to the power n minus 1. Well, first observe that for n bigger than or equal to 1, this guy downstairs is always positive, right? The least it gets is 1, and hence the whole thing is going to be positive because upstairs is positive. So this is a series whose terms are positive, correct? So we're going to use the limit comparison test, and I want to compare it with 1 divided by the leading or the dominating term downstairs, which is 2 to power n as n goes to infinity, right? Gonna compare it with 1 divided by 2 to power n. So example 3. So we compare, so we use the limit comparison test, LCT. With the series so the given one and this one, right? Okay. So obviously each term here is positive. So each term here is a positive term. And each term here is positive for all n, right? Okay. So now what I'm going to do is I'm going to take the limit as n goes to infinity of an divided by bn. So what am I doing again? I'm using the limit comparison test. So I'm checking if the limit of this quotient, the quotient of the terms as n goes to infinity, is positive and finite. So that's what I'm doing. So it doesn't matter which one is an, obviously, and which one is bn. Doesn't matter. Let's take 1 over 2n minus 1 upstairs divided by 1 over 2n downstairs. And this is the same as the limit as n goes to infinity of 2n divided by 2n minus 1, which is the same as the limit as n goes to infinity of 1 divided by 1 minus 2 to power negative n, right? Okay. And n, as n goes to infinity, this term goes to 0, so the limit is 1. Correct? As n goes to infinity, this goes to 0. And hence that whole thing is going to go to 1 over 1, which is 1. Okay? The limit comparison test tells me if this number is positive and finite, this number turns out to be 1. Certainly this is between 0 and infinity. If that's the case, then the two series have the same nature. So they're either both convergent or both divergent. Well, what do you know about this series? This is a geometric series whose first term is 1/2 and common ratio is also a half. Since the absolute value of the common ratio is less than 1, that's going to be a convergent series. Okay? Since this is a convergent geometric series, right? The given series, so the series in question, which is this, is also convergent. By the limit comparison test. Correct? Okay. All right, the last one, example 4. Determine whether the series whose terms are 2n squared plus 3n divided by square root of 5 plus n power 5 converge or diverge. Okay. So as we did for an example 3, I'm gonna take, so I'm gonna realize first that this term is positive, right? this term is positive for all n, clearly. And I'm gonna compare it to another series, which I know if it's gonna converge or diverge, whose terms are also positive, and I'm gonna employ the limit comparison test to deduce whether this is gonna converge or diverge. And who's that series that I'm gonna compare it to using the limit comparison test? Well, I'm gonna take the leading or the dominant term upstairs, which is 2n squared, and the dominant term downstairs, which is n to the power 5. Correct? So I'm gonna use, let me just write it here, example 4. So we're gonna use the limit comparison test with the series I'm gonna take the dominant term upstairs, which is 2n squared, and the dominant term downstairs, which is square root of n5. Correct? All right. And what is this series again? What is this term? You can actually simplify this writing. This is the same as 2n squared divided by n to the power 5 over 2, right? Which is the same as 2 divided by square root of n, or n to the power half. Correct? You subtract, so the larger one is downstairs, so 5 over 2 minus 2 is half. Okay? So this series is simply the series whose terms are 2 divided by n half. Okay? Alright, so now I'm gonna take the limit as n goes to infinity of the an divided by bn, right? This is what the limit comparison test says. Take the limit of the quotient. So I'm gonna take this, let's say, as an, and this as bn. So let me copy. 2n squared plus, so 2n squared plus 3n divided by square root of 5 plus n squared, and 5. And the downstairs is bn, so 2 over n to the power half. Okay. Alright, so I'm gonna let you complete the details. This is gonna be exactly, I mean, it was chosen so that this whole thing behaves exactly as this thing as n goes to infinity, right? So this is gonna be 1. And 1 is a number that's finite and positive. So by the limit comparison test, the series in question is of the same nature right? By same nature, I probably haven't defined it, but I mean that they either both converge or both diverge. So it's the same nature as the series whose terms are 2 divided by n to the power half. And what do you know about this series? What do you know about this series? This is 2 times the series 1 over n to the power half, right? So 2 times this. So the series in question and this one, so technically this one, have the same nature. Well, this is a series that's gonna diverge by the p series, right? By the p series test. This is a p series whose p is half, and this is divergent. So, however, this is a divergent series. Correct? This is a p series, to be precise, with p less than 1. Correct? Less than or equal to 1. Okay. So what can we say at the end of the day? The given series, the series in question, is divergent. Okay. All right. So that should do it. That's the end of this section.